Welcome back to our two-part series. It was to be a third, but we'll do the third as direct instruction in the classroom. So second part of a two-part series on vectors in 3-space. What we're going to begin with is the magnitude of Cartesian vectors in 3-space. So do recall that we had just looked at the plotting of a vector in 3-space centered at the origin. So here we have a very similar looking diagram. Okay, and what we're going to do is we're going to draw in a vector, and we'll call it again the vector OP. So from the origin to the point P. So we'll label this as O. The endpoint, okay, this is not a vector notation or for a Cartesian vector, but rather the endpoint, which we have here, that is point P, has coordinates A, B, and C. So as not to confuse or to mix the notations for the endpoints along with vector notations, what I'm going to do is we're going to denote some other vectors here. So we have in the positive x direction, let's call this one, why not call it PQR, so OQ. And we have this one over here, of course, which is in the positive y direction. So what we'll do is we're going to translate that vector to here. Let's give this endpoint R, and followed by this one over here, of course, C, which translates to here. Let's call that, in this case, S, if you will. Okay? So in order for us to find the magnitude of OS, let's go back for a moment to see how we ended up plotting the Cartesian vector OP. Okay, first step, of course, okay, was to work with this vector here. Okay, so I'm just going to highlight this a little bit more. Okay, we started here, and then of course to that we added this. Okay, now if we only look at the sum of those two vectors in in 3-space and simply along the xy plane. Okay, so envision the xy plane, that's strictly all we're looking at. Really, the length or the vector that we're after is the vector OR. Okay, so we would actually like to begin by finding the magnitude of OR. Okay, also recognizing the fact that that those vectors are perpendicular or orthogonal to one another. That is, there's a right angle between them. So what we should do is begin with that triangle, OQR, which we see here, and use the Pythagorean theorem to develop a relationship for the length of the vector OR. So OR, in this case, its magnitude squared is going to be none other than the sum of OQ and OR. Okay? That is OQ squared plus QR squared. And given the notations we have for x and y of our endpoints, that's nothing more than a squared plus b squared. Okay? Now we move on and we take the magnitude of that vector, okay, and recognize that again we have a right angle here between the blue vector and the vector that has been translated, the upright vector from the origin. And what we're going to do is we're going to use it along with this vector here to calculate the magnitude of the vector OP. So again, we're looking at the upright triangle here. Okay, and we're going to work with triangle ORS. Okay. So in this case, the magnitude of the vector OP okay, so OP squared is going to be the result that we just arrived at, or that we just determined, which is OR we'll take the square of that, and to that we will add the square of the vector RP. Okay? So notice that I do have the point S here. That point, that's redundant. We don't need that notation, right? As the endpoint has been labeled with P. So let's get rid of that to make that clear. So to that we're adding RP and the square of it. So recall that from above, OR squared was A squared plus B squared. And given that C is the Z component, okay, so the point P is actually Z units above the point R, or Z units above the XY plane, we'll be adding on C squared. So therefore, if we are after the magnitude of the vector OP and not OP squared, then we'll take the square root of A squared plus B squared plus C squared. So you can very well imagine that in some of the problems you'll be faced with, you'll need to determine the magnitude of vectors in 3-space. So moving on. Other things that are oftentimes a necessity, and you saw this when dealing with the dot product, okay, was the concept of unit vectors. Okay, so dot product, specifically with projections or vector projections, we needed unit vectors in order to assign direction to the projections. So this idea will come back a little bit later on in the unit. So it's a good time to look at it given that we're dealing with three-dimensional vectors. So we have 2 points given to us. So these would be the endpoints of the geometric vector AB. And in order to make it a position vector, we would have to subtract the corresponding components of the endpoints A and B. So the first thing we need to do, and the reason why I'm aiming at this, is let's say that U or V or whatever letter you like, let U be a unit vector in the direction of AB. And we know from a previous lesson that the unit vector, okay, is going to be denoted by a certain multiple or scalar multiple of the vector AB. And in this case, and in all cases for unit vectors, like we had seen in the previous lesson, that we would scale or multiply it by 1 over the magnitude of the vector AB. So we're going to have to go forward on this and determine a representation for AB. Okay, so I'm just going to switch colors to differentiate between the steps we're taking. So the vector AB, let's take a look at that. So what we'll need to do is to subtract the x components. Okay, so in this case we'd have 3 minus minus 1. That takes care of the x's. The y's, 6 minus 0, and the z's, minus 1 minus 5. So what do we have? Well, 3 minus minus 1 is 4, followed by a 6, and then followed by a minus 6. So let's just double check that we've made some correct moves here. And yes, those values are correct. So that means that we can move forward in defining our unit vector. The only thing that we do need is the magnitude. And as you saw in the previous example, the magnitude of any particular vector in 3-space is going to be the root of the squares of each of the components. So 4 squared, 6 squared, plus minus 6 squared. So we're going to have 16 and 2 36s, so that's 72. So what do we have here? We have a total of 88. Okay, so root 88. Now you're more than welcome to break that down into a mixed radical. So that would be the root of 4 by 22, which is 2 root 22. Okay, so therefore, our unit vector, call it u, which we have said is 1 over the magnitude of AB multiplied by AB, is going to be 1 over 2 root 22 and multiplied by the vector representation 4, 6 minus 6. And we'll just double check that we've got those coordinates correct. And yes, we do. Now, last but not least, we could leave it that way, or we could go one step further and simplify. Do recall, okay, that if you have a particular representation, say u is equal to kv, okay, where v would happen to be, say, in general, v1, v2, v3, then kv is also going to be equal to kv1, kv2, followed by kv3. Okay, so we're allowed to distribute that scalar into each of the components of our vector. So with that being said, what we're going to end up with would be 4 over 2 root 22, followed by 6 over 2 root 22, and lastly, minus 6 over 2 root 22. Moving forward one more step, we'll just simplify and knock out the 2's in the denominators. So we'll have 2 over root 22, 3 over root 22, and minus 3 over root 22. So this would be the endpoint for a unit vector to the vector AB in 3 space. Now, next up, what do we have for you? We do have quite a bit, I believe, left over. Let me just check here for a second. So collinear vectors. Yeah, let's do one more. We'll save collinear vectors for class. Let's just have a look at practicing the dot product for vectors that are in 3 space. Okay, and it's very much the same as what we had beforehand in dealing with vectors in 2 space. Okay, so there isn't a whole lot more that is new there. So in fact, you could look up a generalization or a definition of some kind through your textbook. Okay, but if we just take this example quite quickly, the dot product UV, okay, so in general, it's simply going to look like we would have U1 V1 plus U2 V2 plus U3 V3. So beforehand, when we were working in 2-dimensional space, recall that we simply would have had these, okay? And now that we're in 3 space, we're going to have all 3, okay? So let's add in the values. So we'll have 3 by minus 2 plus minus 5 by 0 plus 2 by minus 6. And recall that the dot product produces a scalar quantity. And in some contexts, you were determining missing angles, as well as proving if 2 vectors were perpendicular to each other. So the dot product will become important to us again as we look at the next vector form of multiplication known as the cross product. So in total, it looks like we have minus 18 as the dot product of the vectors u and v in 3 space. And that, ladies and gentlemen, ends the second part of our 2-part series. The rest we'll cover in class.